Hello, this is Bryan Vakiner. This is my Lab 3, the Black Hole Lab. The objective of the lab was to determine the mass of the black hole given the position and time data of a star in orbit. The only force acting on the star in orbit is gravitational force, so you can use Newton's law of universal gravitation to determine the total net force, and therefore, given the mass of the star, the distance between the star and the black hole, and the moment in the net force, you can determine the mass of that black hole. Another objective of the lab was to analyze the relationship between the force, this force, and its components to the overall momentum. Given the VPython code that I used, this was the mass that I came up with, correct in WebAssign. The contents of the video, I'm going to be discussing the physics principles, my VPython code, where the physics is used, and basically breaking down the forces, their components, and how it relates to the momentum principle. The physics we'll be using is the momentum principle and gravitational force, or Newton's law of universal gravitation. This is the only force acting on the system for this entire lab. Fnet is equal to delta P over delta T, or as I'll be referring to it throughout the video as dP dt. This is the rate of change of momentum and the force. So this is my VPython code. Have the given inputs, the mass of the star, the origin position. The origin is the black hole, and the value g for whenever I calculate the net force. Come down here, and this line of code will read in the CSV file containing the position and time data for the star. The first while loop in the VPython code deals with basically tracking the trajectory of the star as it orbits the black hole. Physics really comes into play with the second while loop, where we will be calculating the change in velocity and the change in momentum in order to figure out the parallel and perpendicular components of dP dt and relating that to the net force. So here we are figuring out the initial and final velocities. Once we have that, we can use that to determine the initial and final momentums. And using these two previous calculations, we will get the variables delta v and delta p, change in velocity and change in time respectively. dP dt is equal to delta p over delta t. That is dP dt. Per Newton's second law of momentum principle, Fnet is equal to dP dt. This line of code is calculating dP dt parallel, the parallel component of dP dt. We use p hat, the direction of the momentum is calculated by the initial momentum divided by the magnitude of the initial momentum. The magnitude of dP dt is equal to just the magnitude of the change in momentum divided by delta t, and dP dt parallel is equal to the magnitude of dP dt times the direction vector p hat. We know Newton's second law, Fnet parallel is equal to dP dt parallel. Here, dP dt is equal to the parallel and perpendicular components added together. So given dP dt and dP dt parallel, we can find the perpendicular component by subtracting the parallel from dP dt. Again, Fnet perpendicular is equal to dP dt perpendicular. This portion of the code is where I've actually mapped out, or rather calculated the mass of the black hole. Black hole is equal to the magnitude of the force times the magnitude of the distance between the two of them squared, divided by the gravitational constant times the star's mass. This comes from Newton's law of universal gravitation manipulated to give you the output mass. So go ahead and run. But that you have black arrow is the parallel component, blue is the perpendicular, and yellow is the net force, always pointing towards the black hole. The questions posed by the lab was, what does it mean? I asked to relate the Fnet perpendicular and dP dt perpendicular and Fnet parallel to dP dt parallel. They are all the same forces. As you can see, dP dt is equal to Fnet, dP dt perpendicular is equal to Fnet perpendicular, and dP dt parallel is equal to Fnet parallel as well. The difference arises in the way you calculate them. Fnet is calculated using Newton's law of universal gravitation, while dP dt is determined using the change in velocity with respect to time. Fnet and its components give us information on how the star's motion is going to be affected, whereas dP dt describes the motion itself and how it is changing. dP dt parallel determines speeding up or slowing down, while dP dt perpendicular indicates a change in direction. Fnet is simply a description of the force on the object and how it is affected. The what if question is if the black hole whose mass you found was removed and a different one was placed in the same location, if the star's movement is unchanged, there would be no change in the mass of the black hole. They are directly proportional. If you would be able to tell a difference, I mean, there would be no difference because you wouldn't be able to change the mass of the black hole that the star is surrounding without changing the mass of the star or the distance between the two. And if you change either one of those, it would not be the same problem, and it would not be an unchanged path. So there it has it. There's my lab 3 for physics. Thank you very much for watching.